Hello friends, welcome back to my YouTube channel. In the previous lecture, we discussed the step-by-step procedure for designing a laterally supported beam. In this lecture, we are going to take a numerical example and we are going to design this beam manually and then verify the results in STAADPro software. Please stay tuned as this kind of content is not available on any other YouTube channel. So here I am taking an example of a laterally supported beam of length 1.8 meter. Okay, and it is subjected to a concentrated load of 500 kilonewton at the center. Okay, so this is a beam. You can see that the beam is laterally supported over here. Okay, it is restricted from moving in the lateral direction. Okay, I will show this in STAADPro as well. Okay, and we need to design this beam. Okay, this beam is ISMB 400. This beam is ISMB 400 beam. Okay, now let's design this beam. Okay, so here I am using Excel sheet to design this beam manually. So here you can see that our member size is ISMB 400. Okay, the load that is acting on it is 500 kilonewton. Length of the member is 1800 mm. Okay, depth of the cross section is ISMB 400, so it will be 400 mm. Okay, width of the flange is 140. Thickness of web is 8.9. Thickness of flange is 16 mm, and yield stress is 250 megapascal. You can get all these values from the steel table. Okay, now let's first calculate the clear web depth. So clear web depth will be nothing but the total depth, that is 400 minus 2 times of the flange thickness. So that is 368 mm. Now first step is to classify the section. So we will first classify the flange. So B by TF value. What is B? B is nothing but half of the flange width. So in our case 140 by 2. B is 70 mm and divided by TF. What is TF? Thickness of flange, which is 16 mm. So in our case, B by TF is 4.375. Okay. So it is less than 9.4, 9.4E, right? So it is plastic. Similarly, web, we need to calculate the ratio of D by TW. What is D? D is nothing but total depth 400 minus 2 times of the flange thickness, right? And divided by the thickness of web, which is TW. So my D by TW value is 41.35. Okay, and this value is less than 84E. So again my web is plastic. So since both flange and web are plastic, my cross section will be plastic. Okay, now let's calculate the shear capacity. Why? Because first of all we need to compare what is the shear force that is acting on that beam. Okay, and what is the shear capacity. Okay, then we can categorize it as low shear or high shear. So let's calculate the shear capacity. So what is the area of web? Area of web is H into TW. Okay, what is H? H is nothing but the height of the web and multiplied by the thickness of web, which is 8.9 times of 400. So this will be 3560 mm square. Gamma MO, that is partial safety factor, it is 1.1. So shear capacity VD is given by this formula, that is AVFI upon root 3 gamma MO. Okay, so my design shear capacity is 467.13 kilonewton. And what is my acting shear? Okay, as you know that since it is a simply supported beam and if a load is acting at the center, what is the shear force at the supports? It is half of the load, right? V is equal to P by 2 at each support, right? So acting shear force at the support is 250 kilonewton. And if you compare, 250 is less than 0.6 of VD, right? 0.6 VD is 280. Okay. So since V is less than 0.6 VD, we can categorize this as a low shear case. So for the low shear case, what is the formula for design bending capacity? So it is MD is beta B ZP Fi by gamma MO. What is ZP? plastic section modulus. Why we are using ZP? Because since our section is a plastic section, so we need to calculate the plastic section modulus ZP. So ZP is given by summation of AI into YI. Okay, what is AI? AI is nothing but the area of the section. So what we are doing is we are going to divide our I section at the center into two halves, and we will calculate the summation of AI into YI for the upper half, and we will multiply it by 2 since the section is symmetrical. Okay, so let's calculate the area of flange first. So area of flange will be nothing but the width of the flange into thickness of the flange. Okay, so 140 into 16, this will be the area of flange. Now distance YF. What is this YF? YF is nothing but YF. So if this is our I section, okay, from the center to the center of this flange, this distance is YF. Okay, so what will how to calculate this distance? So half of this will be this much, okay, and minus half of this flange thickness. So we'll get this distance. Okay, so that is what I have done. YF is nothing but h by 2 minus TF by 2. So that will come out to be 192 mm. Similarly, we need to also calculate the half of the web. Now, half of the web area. So how to calculate the half of the web area? That will be equal to 400 by 2, right, minus thickness of flange into thickness of web. So how I got this? This is total is 400. Okay, so 400 by 2 will be this much. Okay, and minus this flange thickness, so it will be this. So it will be, I am calculating this area. Okay, initially I calculated this area, that is area of flange. Then I calculated this area, that is half of the web. Okay, so this is my half of the web area. Okay, then I need to also calculate YW as well. So what will be YW? So again, if this is my I section, this is my neutral axis. Okay, so this, since we are calculating area, we calculated area of this. So center of this will be my YW. So this will distance will be YW. Okay, so I have calculated this value. So how to calculate this? That will be total depth, that is 400 divided by 2, and minus the flange thickness, and that overall value divided by 2, right? That is this total, that is h by 2. Okay, I will subtract this, so I will get this height, and this height divided by 2 will be my YW. Okay, so then my plastic section modulus will be summation of AI into YI, and I will multiply it overall value by 2 since the section is symmetrical. Okay, so I will get my plastic section modulus as 11611478.4 mm cube. Okay, now if you see in the section, in the steel table, this section modulus value is slightly more than this value. If it is here, it is 1161, here it is 1176. So why this difference is there? Because we have not considered the root radius in this calculation. So in order to exactly match the value, instead we are using this value of the steel table. Okay, so if you put in this formula MD, that is beta B ZP Fi by gamma MO. Beta B obviously it is 1 for the plastic section. Okay, and my ZP is 1161. Okay, so through this formula MD will be equal to 267.32 kilonewton meter. Okay. Okay. Now let's calculate the utilization ratio. So first of all, what is the maximum moment? So as you know that in case of simply supported beam, okay, this is our simply supported beam, and as you know that load is acting at the center, that is P, which is in our case it is 500, right? So maximum moment will be at the center, right? That you already know. That will be PL by 4. Okay. So this acting moment is PL by 4. P, as you know, it is 500 kilonewton and length of the beam is 1800 mm. Okay. And divided by 4. So this value will be 225 kilonewton meter. So what will be your utilization ratio? That will be M upon MD, that is acting moment, divided by the design strength. Okay. So this will be 225 divided by MD, which is 267.32. So this is the utilization ratio that we are getting from the manual calculations, that is 0.85. Now let's model this beam instead. Okay. So here you can see this is the beam that I have modeled. Okay. I have applied a load of 500 kilonewton at the center. The length of the beam is 1.8 meters. Okay. And the section size is ISMB 400. Okay. Let me show you the support condition as well. So one end I have kept it as pin support, and one end I have assigned a fixed butt support. Okay. So in that fixed butt support I am providing a roller support. So in order to provide a roller support, I am allowing the moment in the X direction, that is along the length of the beam. So I have released Fx, and since this beam is a pin support, so I am releasing all the moments as well, Mx, My and Mz. However, since we are designing a restrained beam, okay, a laterally supported beam, so I am not releasing Fy and Fz. So I am restraining the beam in the Y and the Z direction, that is in the vertical as well as in the lateral direction. So that is a laterally supported beam. Okay. And I also assigned the design parameters, as you can see. Okay. Code is ISN 800. Fu, that is ultimate strength, is 410 megapascal. Okay. I also assigned lat 1. So lat 1 is nothing but the beam is laterally supported. Okay. And track 2 in order to view the complete design result and check code. Okay. Now let's run this file. Okay. Go to the post processing, and if you check the utilization ratio, it is 0.84. Okay. So in our case, from the manual calculation we got as 0.85, from the stat it is 0.842, so it is almost matching with the stat value. Okay. So difference is close to 0, so it is around 0.94%. So guys, this is how we can design the laterally supported beam. That's all for this video. Thanks for watching. Bye for now.